This is going to be the Chapter 5 Atomic Structure lecture for first year chemistry. The first thing that we talk about in Chapter 5 is the theory of the atom, and it was started by Democritus, a famous Greek teacher who lived in the 4th century BC, and he first suggested the idea of the atom by doing sort of a thought experiment. He considered if you had, let's say, a piece of gold and you continue to cut that piece of gold into smaller and smaller chunks, you would get down to a piece of gold that wouldn't be divisible. And so he called this smallest piece of matter that you can't divide the atom. It's from the Greek word atomos, which means indivisible. And then later on, in the 18th century, or the 1800s, I'm sorry. In the 1800s, John Dalton came up with his atomic theory based on results of his experiment, and Dalton's atomic theory has basically 4 main parts to it. He first said that all elements are composed of tiny particles called the atom that he got from Democritus. He also suggested that atoms of different elements were different from each other, so instead of there being one type of atom, there would be a different atom for each element. And then he said that atoms would combine in small whole number ratios to form compounds instead of fractions of atoms or large amounts of atoms making compounds. So that's why water has a formula of H2O. The ratio of hydrogen to oxygen is a small ratio of 2 to 1. Or glucose, for example, is a ratio of 6 carbons and 12 hydrogens and 6 oxygens. So you have small whole number ratios of atoms when they make compounds. Another thing that he said was that in a chemical reaction, the atoms can separate from one another, they can join with other atoms, or they can rearrange, but they're not going to change from one element into another. Then we discuss the parts of the atom. We're going to talk about the particles that are in the atom. So the atom is basically defined as the smallest particle of an element that can exist. There are smaller particles, but they can't exist under normal laboratory conditions. The 3 subatomic particles that are in an atom are the electron, the proton, and the neutron. So the electron was discovered by J.J. Thomson in 1897, and the electron has a negative charge, and its mass is very, very, very small compared to the other 2 particles. It's about 2,000 times smaller than a proton or a neutron. So we usually just ignore the mass of the electron. The electron is what's responsible for making chemical bonds with another element to form compounds. So the electron on the outside of the atom is what is involved in making chemical bonds. The proton has a positive charge, and it was discovered in 1886 by a guy with the name E. Goldstein. Our textbook doesn't have his first name. I think it's Ernest, but I could be wrong. And again, the proton is a lot more massive than the electron. And the proton is what gives the atom its characteristic difference from any other atom. So if you change the protons, you're basically changing the element. On the next slide we have the neutron. The neutron does not have a charge, that's why it's neutral. So the neutron gets its name from the word neutral. And it was discovered in 1932 by James Chadwick. And the neutron has about the same mass as the proton. And again, the neutron and the proton are around 2,000 times heavier than an electron, so you don't really need to worry about the electron's mass, only the neutron and the proton. And the neutron is basically the glue that keeps the nucleus from falling apart. Typically, if you had 2 protons right next to each other, their positive charges would repel, but because the neutrons are in there, they form a very, very strong nuclear force, is what it's called, and it glues the nucleus together. So you need neutrons in order for the nucleus to be stable. These 3 particles make up all the visible matter in the universe, and what I mean by visible matter would be solids, liquids, and gases, are 3 phases of matter. There are other particles that exist, and there's stuff like antimatter, but we're not going to concern ourselves with that in first year chemistry. Then for the atomic structure, we discussed that the nucleus is the center, and it contains the protons and the neutrons, so the nucleus has a positive charge, and we'll discuss the discovery of the nucleus in a little bit. And the electron cloud surrounds the nucleus, and that's just what the picture shows. On the next page we discuss the person who discovered the nucleus. His name is Ernest Rutherford. He discovered it in 1911, and the technique that he used is that he shot alpha particles, which came from the element polonium, through a thin sheet of gold foil. And an alpha particle happens to be a helium nucleus, so it contains 2 protons and 2 neutrons glued together. And so he shot those alpha particles from polonium through a piece of gold foil, and most of the particles went through to the detector, and some were slightly deflected, and some even bounced back. And it was the ones that bounced back that surprised him the most. And so his quote from a video we watched during class was, "It would be like shooting a a 15-inch shell or a cannonball at a piece of tissue paper and having it bounce off. So these particles that bounced off of the gold foil, he had to assume hit something very massive and very small because most of them missed it. And he also assumed that it had a positive charge. So this was the nucleus that he discovered. The next slide just shows a picture of the apparatus that he used. The conclusions about the nucleus are as follows. Most of the atom is more or less empty space. The nucleus is about 10,000 times smaller than the atom itself. So the electron cloud takes up much, much, much more space than the nucleus. And again, it's about 10,000 times smaller than the atom itself. So the nucleus is very tiny, and the stadium analogy that I have here in the notes would be like if you put like a shot put or some really, really heavy object like a bowling ball in the center of a football stadium. The bulk of the stadium would be the electron cloud, and that very heavy object like a bowling ball or shot put would be the nucleus. And for an analogy, a marble might represent the electron flying around the stadium. For number 3, the nucleus is very dense, and again that just means there's a large mass in a very small volume, and the nucleus is positively charged because it contains the protons. Then I give the students a periodic table and I point out what the atomic number on the periodic table refers to. The atomic number is the whole number that's on the periodic table, and it numbers each element. So hydrogen is element number 1, helium is element number 2, and so on. And that stands for the number of protons that are in the nucleus. The mass number of an element has to be told to the students because it's not on our periodic tables. The mass number is the sum of the protons and the neutrons in the nucleus. And because protons and neutrons are the particles that have mass, it makes sense that they would be called the mass number. So you add them up, and that's the mass number for the element. In a neutral atom, the number of protons and the number of electrons are equal to one another. And we're not going to talk about ions in this particular chapter, so we're always going to have the protons and the electrons equaling each other. And if you want to calculate the number of neutrons, you have to be told the atomic number and the mass number, and all you need to do is subtract them. If you subtract the atomic number from the mass number, you're basically subtracting out the protons from the nucleus, and you're left with the mass of, you're left with the neutrons. So subtracting the atomic from the mass, you get the neutrons. Then we do some practice problems. I give them sodium with a mass number of 23, and if you look up sodium on the periodic table, it's number 11. So there's 11 protons and 11 electrons because this is a neutral sodium atom. And when you subtract the mass and the atomic number, you get 12 neutrons that are found in the center. For example number 2, we have uranium. It happened to have a mass of 238. Its atomic number is 92 on the chart, so it has 92 protons and electrons, and when you subtract, you get the neutrons of 146. There's other uraniums out there. There's uranium that weighs 235, but this one, because it weighs 238, has 146 neutrons. And then I give them the atomic number, which is determined from the number of electrons, which has to equal the number of protons if this atom is neutral. And then I give them the neutrons, so you can figure out that it's going to have a mass number of 31. So with an atomic number of 15 and a mass number of 31, this happens to be phosphorus 31. Phosphorus with a mass number 31. Then I discuss isotopes. An isotope refers to atoms that have the same number of protons but they have different masses or different number of neutrons. So when the mass is different but the protons are the same, those are called isotopes. So it's exactly the same element, but it just happens to weigh different. So the examples that I have are carbon-12 and carbon-13. It's the same element, carbon, because it has 6 protons in the nucleus, but carbon-12 only has 6 neutrons, where carbon-13 has 1 extra neutron, makes it a little heavier. There's a little extra glue in the nucleus. For example number 2, we have chlorine-35 and chlorine-37. It happens that there isn't any chlorine-36 on the Earth. It's just chlorine-35 or chlorine-37. The numbers 35 and 37 again refer to the mass number. So for each example up above, the elements have identical atomic numbers. So carbon is 6 and 6. Chlorine would be 17 protons, no matter if it's chlorine-35 or chlorine-37. So the number of protons is the same, but the mass number is different. There's another way to write the isotope with a number on top and a number on bottom. The mass number is on top and the protons are on bottom, so when you subtract those numbers as written, like 12 minus 6 or 35 minus 17, you would get the number of neutrons. That's a very convenient way to write the symbols because it's kind of lined up already to subtract them. And then we do some more practice problems. Xenon weighing 131, or a mass number of 131. would have 54 protons and 54 electrons, because that's the number off the periodic table. That's the atomic number. And then again, subtracting, you get 77 neutrons in the center. For example number 2, we have copper 63. Its element number 29, as stated on the periodic table. Also, the bottom number in this format is the atomic number. And then when you subtract, you can get the neutrons of 34. And then for example number 3, I have them go backwards, where I give them the protons, neutrons, and electrons, and they have to determine the element. Because the protons is 1 and the electrons happen to be 1, this is element number 1, which is hydrogen. And since it doesn't have any neutrons, this would only have a mass number of 1, because there's only one particle in the center. So you could write the symbol as H-1, or the other format would be H and then a 1 on top and a 1 on bottom. Before I talk about atomic mass, I kind of make a joke to my students in class that isotopes are kind of like Oprah Winfrey. She was heavy, and then she was thin, and then she's kind of getting heavy again. And so I make the joke that an isotope is basically an element that's, you know, fat or skinny, but it's still the same element. So I joke with them and call it an isotopera. So an isotopera in honor of Oprah Winfrey. Anyway, now we're talking about atomic mass. Based on the relative masses of carbon-12, all the other elements are related to that element. So atomic mass is always based on one particular isotope, and it's carbon-12. And they decided that they wanted its mass to be exactly 12. And if you take carbon's mass, carbon-12, and it has a mass of exactly 12, then you're dealing with protons that weigh about 1 atomic mass unit, and that's just the label on the numbers. And it has a neutron mass of around 1 atomic mass unit. And as I mentioned before, electrons don't hardly weigh anything, so we consider them 0 atomic mass units if you want to just round it off. So all the masses on the periodic table are compared to how much carbon-12 weighs. So for example, if you're twice as heavy as a carbon-12 isotope, you would have an atomic mass of around 24. Or if you weigh 1/3 the mass of carbon-12, you would have an atomic mass of around 4. So all the weights on the periodic table are compared to carbon-12, which has been designated with a mass of exactly 12. Now, if you look at a periodic table, the numbers that are standing for the atomic weights are not whole numbers, they're decimal numbers. Even for carbon, it has an atomic weight of 12.011, and that's because this is a weighted average. And I'll just simply define a weighted average as this. You basically have to take into account how many particles of an atom are present under what percentages, and how much does it weigh. So for example, I use an example later in the notes about chlorine. Chlorine comes in the two isotopes 35 and 37, so you'd have to take the abundance of chlorine 35 and the abundance of chlorine 37 and find an average. And since they don't come into 50-50 percentages, you're not going to get an average of exactly 36. It's actually weighted closer to 35. So there's about every 3 and 4 chlorine atoms in the world are chlorine 35, and every 1 out of 4 atoms would be chlorine 37. So there's a weighted average that you find on the periodic table. So that's basically what we're going to be doing in this next calculation. We're going to find the weighted average, and I start with an example of grades, because the students are familiar with our weighted averages with our district's grading policy. For example, we have major grades. Let's say they're 60% of your grade, and a minor grade would maybe, like a homework grade, would only be 30% of your grade, and then when it comes to the semester exam, that might be weighted only 10% of your grade. So let's say we have a geometry teacher who has her categories as 60%, 30%, and 10%. And let's say the student scores major grades, that would be like tests and stuff like that, 80%, and then minor grades 60, and then the semester exam he gets a 65. So we're going to calculate what their overall grade would be if they're weighted. So basically what you're going to do is 2 steps. You're going to multiply each score by the percent that it's weighted, and then you're just going to add them up. So I show the calculation on the screen. You multiply them together. When you add up these answers, you end up getting the weighted average, and the weighted average is 72.5, which would be a C. Now a normal average would be if they're all weighted the same, so 33%, 33%, and 33%. If you multiply them and add them up, you would get an average of only 68.3. Now, normally what you would do if you're just finding a normal average is just add them up and divide by 3. But if you wanted to do the calculation as shown up above, you would have to assume that all the percentages were exactly 33.3%. So I just add them up and divide by 3. It's a lot quicker than multiplying by 33% and then adding them up, but you still get the same answer. So you can see that if you do a normal average, you get a 68, but if you get a weighted average where you scored higher on tests, and tests were 60% of your grade, that's going to boost it up a little bit so you can get a C in the class instead of a D. On the next screen we do weighted averages of isotopes. So again, I was using the example of chlorine 35 and chlorine 37. You can see the percentages here. 75.8% of all the chlorine in the world is chlorine 35, and then 24.23% is chlorine that weighs 37. So if you wanted to figure out the weighted average atomic mass of chlorine, you would multiply the percentages times their mass numbers and then add up the answers. And you get a weighted average of about, let's see, 35.4951 AMUs, and AMU stands for an atomic mass unit, and that's just the label on atomic masses. In the last example we have oxygen. It comes in 3 isotopes: oxygen 16, oxygen 17, and oxygen 18. And again, oxygen 16 has 8 protons and 8 neutrons, and oxygen 17 also has the 8 protons, but it has 1 more neutron. And oxygen 18 again has the 8 protons, that makes it oxygen, but it has 2 extra neutrons, which makes it have a mass number of 18. And most of the oxygen in the world is oxygen 16, so if you're going to estimate oxygen's average atomic mass, you would say that it's going to be pretty close to 16, maybe just a little bit more because of 17 and 18. So I put down as an answer of barely over 16 AMUs.